Welcome to this video on nuclear reactions, looking at fission and fusion reactions and how energy is created in these reactions. So what are we learning today? What happens in a fission and a fusion reaction? To be able to state which reactions for fission are spontaneous or induced. To explain using probably the most famous physics equation, E equals mc squared, how the energy is produced by nuclear reactions due to the difference in mass between the reactants and the products, the energy mass equivalence. And to be able to carry out calculations using E equals mc squared for both fission and fusion reactions. So let's start with nuclear fission. Now we have already met nuclear fission and nuclear fusion for National 5, so the basics of the reactions should be something that you're already familiar with. So fission is the splitting of a large nucleus into two smaller nuclei. And there are two different types that we're going to discuss at higher, what's called spontaneous and induced fission. So if you think about those words, spontaneous, if you have a spontaneous party, you just have a party without any preparation. If you think about the word induced, apart from being used in physics for inducing a current, it's also used to when you're talking about inducing the birth of a baby. So you're making something happen is what that means. So the spontaneous reaction is something that just happens, and an induced reaction is something that you cause to take place. So in spontaneous fission, a nucleus breaks down without any underlying cause. We've not made it happen, it just happens. And this could be a large nuclei splitting into two smaller nuclei, or it could be a large one split into different sizes of nuclei. They don't have to be the same size. The picture at the top right there shows similar sizes, but it doesn't need to be like that. This happens with heavy and unstable, particularly some certain types of man-made isotopes as well. So we have a large nucleus and we have two smaller nuclei, and we can see a reaction below there. And within these reactions we get energy produced as well. In an induced fission reaction, a nucleus is hit with a neutron. This type of reaction is what takes place in a nuclear reactor in a power station or a submarine. And we fire a neutron at a uranium nucleus, causing it to split into two parts, releasing more neutrons and energy. So an induced fission reaction will start with a neutron, whereas a spontaneous fission reaction will just start with the larger nucleus and not have a neutron in the reactants, the things before the arrow on the left-hand side of the equation. Okay, commonly it's shown in a picture a bit like this one. So we've got the neutron, the little blue thing on the left there, hitting the larger nucleus made up of protons and neutrons, and then that's splitting into two smaller nuclei shown at the top and the bottom, and we've got three neutrons and some energy being produced. Those neutrons can then go on and cause further induced fission reactions in what's called a chain reaction. In a nuclear reaction, as we saw in the earlier section, the mass number and the atomic number are conserved. But we do find that the total mass of the reactants before fission or fusion is greater than the total mass of the products. There's a small difference in mass, and that difference in mass is changed into energy. And that's using the famous relationship E equals mc squared. So m is the difference in mass between the reactants and the products. In some books you'll see lost mass. The SQA preferred difference in mass, so that's why we're using that term there. So we take that tiny difference and we multiply it by c squared, c being the speed of light, 3 times 10 to the 8 meters per second. And that turns into energy. So this is called the energy mass equivalence relationship, because it's saying two things that seem quite different, energy and mass, are actually linked together. We mentioned earlier chain reaction, so one fission reaction doesn't produce very much energy, so because we can get more neutrons produced by some fission reactions, those in turn can cause further fission reactions and what's called a chain reaction. So we get lots of small differences in mass from each reaction, and all these convert into energy, and all these energies add up over time. So this is a chain reaction where a fission reaction causes the splitting of the nucleus into two smaller nuclei, releasing energy, more neutrons, and those neutrons then hit more large nuclei to split those into smaller nuclei. Okay, and here's a diagram showing a chain reaction, and each time you're getting a release of energy. This means that the reaction becomes an exponential reaction because you started with 1, you've got 3 reactions after the first one because you've made 3 neutrons, then you've got 9, then you've got 27. So it's getting bigger and bigger, so the reaction can generate quite large amounts of energy and needs to be controlled to make sure it doesn't get too big. If it's not controlled, then it's like a nuclear bomb. If it's controlled, we can absorb those neutrons using some things called control rods in nuclear reactors. So we can slow the neutrons down, we can stop them from causing further fission reactions, and then we can stop the reaction. So here's a little picture of a nuclear reactor. You don't have to know the details of this for higher physics, but given it's one of the applications of nuclear energy, it's worth being a little familiar with what's going on. So the bit on the right is the heat exchanger, and basically the heat exchanger takes the heat from the coolant for the reactor and heats up water to turn it to steam. And then that steam will turn a turbine, which will turn a generator, which will create electricity. Within the reactor itself, you have the uranium fuel rods, you have the coolant surrounding it, which takes the heat away to then heat up the water to turn into steam, and you have this graphite moderator. That's because the nuclear fission reactions only take place when the neutrons are going at the right speed, and graphite slows down the neutrons to be the correct speed for the fission reactions to take place. And we also have these control rods shown in yellow here that can raise and lower, and they can absorb some of the neutrons, stopping the chain reaction and reducing it. So if the control rods are fully inside the reactor, then all the neutrons are absorbed and there's no heat energy produced. Outside the whole thing, there's a concrete thick shield, because thick concrete will absorb most of the nuclear radiation. So really what we have is we have the nuclear fission reactions producing some energy. That energy is coming from the difference in mass between the reactants and the products. That energy heats up the coolant. That coolant then heats up water. The water turns into steam. The steam turns a turbine. The turbine turns a generator to make electricity. So only this part of the nuclear power station has radioactive materials within it. The water itself isn't exposed to nuclear radiation. So here are some of the functions. So we've got the fuel rods made of uranium enriched with uranium-235. We have the moderator to slow down the neutrons to cause more fission reactions. We've got the control rods to absorb more neutrons to prevent the reaction coming out of control. And we've got the coolant to cool down the reactor and stop it from overheating. And the containment vessel, thick concrete, lead lined to absorb neutrons and other types of nuclear radiation. So let's have a look at an example of the kind of calculations you would need to do for higher physics. So here we have a nuclear fission reaction. How can we see that? Well, on the left there we've got a large nucleus, uranium-235, and on the right of the arrow in the product side we've got two smaller nuclei, barium-141 and krypton-92. So that's showing that we've got a nuclear fission reaction because we've got a large nucleus to two smaller nuclei. We've also got an induced reaction because on the left hand side there we have our neutron in the reaction. So if it's a spontaneous reaction, the neutron there on the left wouldn't be there. So this is an induced reaction. And after our reaction, we've got more neutrons and we've got a release of energy. So if we want to work out how much energy is being released by this reaction, we have to work out the mass of all the things before, the uranium and the neutron, and the mass of all the products afterwards, and look at the difference in mass between the two. So within the question, there will be details about what these masses are. And these will be small, so 10 to the minus 27 kilograms typically. When you're doing these calculations, you should never do any rounding of your numbers because that will produce an incorrect answer because the differences are really, really tiny. So you need to use the whole answer within your calculation. Within the question, there will be the mass of the individual nucleus or individual elements listed in a table. Okay, so we've got the mass of uranium plus the mass of one neutron to give us our total before, M1. We've got the mass of the barium and the krypton and 3 neutrons. So if you've got 3 neutrons afterwards, you need to multiply the mass of one neutron by 3. A common mistake is to forget that there's more than one neutron afterwards in some cases, and just to add in the mass of 1. So we have two masses, 391.949 and 391.613 times 10 to the minus 27 kilograms. What do we do next? Well, we take those two totals and we subtract the masses away from each other to get the difference in mass, delta M, and that is the M in the E equals mc squared. So we multiply that mass, the difference in mass between the reactants and the products, what we had before and what we had afterwards, by the speed of light squared, and we get an energy. So in this case 3.0 times 10 to the minus 11 joules per reaction. Now there'll be lots of reactions taking place, which is why we can get lots of energy to heat up the water, to heat up the coolant, which then heats up the water to turn it into steam. So if we're describing nuclear fission and the process of releasing energy, a large nucleus splits into two smaller nuclei. There's a difference in mass between the reactants and the products, and that difference in mass is changed into energy. So sometimes you're asked to explain how energy is produced by a nuclear reaction. Okay, let's remind ourselves about nuclear fusion. So nuclear fusion is the process that takes place in stars and the sun, where energy is released by smaller nuclei joining together to make a larger nucleus. In stars, this is hydrogen nuclei fusing together to make helium. We need very high temperatures and pressures to overcome the repulsive forces between the nuclei, because nuclei made up of protons, and the protons are going to repel. So we need high temperatures and pressures to get them close enough, and then when they are close enough, the strong force will cause the nuclei to join together. Okay, so fusion is two smaller nuclei combining to form a larger nucleus. So when they join together, the final mass is less than the initial mass. So there's a difference in mass between the reactants and the products. And again, the energy that's produced from this reaction can be calculated using E equals mc squared, where m is the difference in mass between the reactants and the products. So here we have details of a nuclear fusion reaction where we have hydrogen nuclei forming together to make helium. Okay, hydrogen, we have two different isotopes there, one called deuterium, which has one proton, one neutron, and one called tritium that has two neutrons and one proton, an isotope of hydrogen. But they're smaller, they join together, they make the helium nucleus that we can see on the right there. We also have a neutron and we have energy produced. So if we're going to work out how much energy is produced by the reaction, we do the same process as before. We look up the masses of the products. So we've got a mass for the hydrogen 2, the deuterium, or the hydrogen 3, the tritium, and we've got one of each of those, so we add those two up together to get our mass before, M1, and then we look at the mass afterwards. We've got the alpha particle, or the helium nucleus, that's there. We've got the neutron, there's only one this time, and we add those up. So we get the mass before and the mass afterwards. We then take those away to get our change in mass, and then that change in mass is multiplied by the speed of light, 3 times 10 to the 8 squared, to give us the energy released in one reaction. So let's just summarize what we've looked at. What happens in a fission and a fusion reaction? So fission is the splitting apart of a larger nucleus into two smaller nuclei. Fusion is the joining together of two small nuclei into one larger nucleus, both releasing energy. We have a spontaneous reaction that just takes place, and we have an induced reaction for fission where we're firing a neutron and causing the fission reaction to take place. And we can see that when we write the equations. The induced reaction has the neutron on the left-hand side with the reactants. And we can explain using E equals mc squared the energy that's produced by nuclear reactions. So we add up the mass of the reactants, we add up the total mass of all the products, we find the difference in mass between those two. We then use that difference in mass times c squared, the speed of light, to work out the energy of one reaction. And we're able to do that for nuclear fission and nuclear fusion reactions.